So with this one, it's a conceptual question here. We can run through kind of what happens. And I'll just go ahead and start by highlighting that most people said B or D to this. So let's just say it's one of those two, and we can see what's happening. We're either having the interval size, or we're dividing it by 1.414. So which one is it? Okay, so it doesn't tell us right now if it's a confidence interval for proportions or for means, but it turns out that doesn't matter. So remember, your confidence interval is determined by your margin of error. And so if we look at the margin of error for proportions, then that is your critical value times the square root of p hat times 1 minus p hat divided by n. And then your margin of error for means is going to be a t star, your t critical value, multiplied times your standard error divided by, or sorry, your standard deviation of the sample divided by the square root of n. Now, if I change this real quick, I'm going to rewrite this as the square root of p hat times 1 minus p hat divided by the square root of n. So in both cases, I could even kind of combine these under, I could move the critical values into the numerator if I want to. So in both cases, I'm basically dividing by the square root of n. So now I can think about this. If I double the sample size, I'm going from n to 2 times n. Now I can separate this as well into square root of 2 times the square root of n for both of these. So it doesn't matter what we're dealing with, if it's means or proportions, we're going to be dividing by the square root of 2. So the correct answer here is dividing by 1.414. Okay, so just an important thing to keep in mind conceptually. We're going to be seeing some other problems like that today. It's all about review, so this is a good way to start it off. Okay, you can see what's going on today. It's just going to be a bunch of practice just a second, I'm making a note real quick. So we're going to be going through if I can think straight, the problem that we left off on Friday. I had you guys kind of left it for you to practice with. We're going to go through it, then 10 multiple choice questions, and then 2 FRQs. I'm going to be going through everything somewhat quickly, as you might expect. So as we're going through it, if there's something that you're not fully understanding, make a note on that, and you can stick around later. We can go over it. The other thing I wanted to do real quick, I'm not going to probably switch back and forth to the formula sheet, so I wanted to do that right now. If I switch back and forth, it messes with the writing and I lose what I've done. So the key thing on the formula sheet, we've already gone over this stuff, but I just want to repeat it. You have your confidence interval general formula right here. So you want to make sure that you can identify that one and you can find it. You don't need to worry about these other things, just a confidence interval. We're going to be working with one population, so we're going to be dealing with the standard error for one proportion, one sample proportion, and the standard error for one sample mean right here. Those are the only formulas you really need to know. Of course, you do need to know whether you're using a Z star or a T star. This is your Z table right here, but we're going down to this. So your T star, your T critical values are all right here in this table, table B, and your Z star is down at the bottom. Remember, use Z star for proportions, T star for means. And I'm not going to be switching back to this to find our critical values as we go through, but you can, okay? So if you want to kind of flip over, have this PDF open on your iPad, then whenever we get to a problem where you might need to look up a critical value, you can flip over here and find it. I'm just going to assume that you know how to do that and show what those critical values are. But again, stick around if you need more help with this aspect of the problem. So just to give you a heads up on what you can expect there. And that is just about it. So we're going to go ahead and get started. And here's the problem that we were left with on Friday. I didn't do it. I'm just going to run through it. So just to say it one last time, I won't necessarily spend adequate time on any one problem. So if there's something that you wanted to go over again and ask some more clarification on, just make note of it. Okay, so a college professor claims that the average number correct on the most recent exam was 18.5. You randomly sampled 30 people in your class and found a sample mean of 17.8 correct and a standard deviation of 2. Okay, so construct a 95% confidence interval for this sample. Pretty straightforward. Now you could just start plugging numbers into a formula, but we want to go through the full 4 steps to show that we have a very clear understanding of the entire process. So the parameter that we are looking for, this is we have sample means. So we're looking for the mean, the population mean. So that is the parameter that we're interested in, which is the true mean number correct. All right, and I'll just call that good. Confidence level here is 95%. Now in this case, it's a mean. It is going to be a T star critical value. And when we have 30 in the sample and we have a 95% critical value, then of course you can find that on the table. I'm just going to do, remember you can also use inverse T on your calculator to solve that. So that's what I'm going to do real quick. I think I know what it is, but I don't quite remember. So just as you're doing this, remember that your degrees of freedom is going to be 1 less than your sample size. It's going to be 29 degrees of freedom. And you end up with a 2.045 critical value. So I'm just noting that right now, but we're not going to use it yet, but we'll have it available when we need it. Okay, the name of the procedure here is going to be a 1 sample a T interval for mu, because we're trying to estimate the population mean. And we're going to check the conditions. We need to make sure it's random, that it meets the 10% condition, and that it is normal. Okay, so is it random? Well, it says it was a random sample. So yes. I'm being a little bit lazy, but what you could do is like write a little paragraph as you go through a problem like this. It says, we have a random sample. It meets the random condition, 10%. Now this one's a little bit trickier. This is maybe just poor wording the way I set it up. But we sampled 30 people. We have to assume that's less than 10%. And you could think on college campuses, there are some classes with hundreds of people in these big lecture halls. So, and maybe there are multiple sections given by the same professor, and he might be teaching 500 plus students this stuff. So it doesn't give us any specific evidence of this. So we're going to assume it has been met, but we might say something to that effect. It's like, we assume that 30 is less than 1/10 of the population size, though we don't know 100% if that's true. We're just gonna operate as though it is true. Okay, and this is maybe worth pointing out right here, that if you ever have a situation where you do not meet one of these conditions, then the random one not being met is going to be a big deal. But if it doesn't meet one of the other 2 conditions, we can just still proceed as normal and make a comment to the effect, we did not meet the 10% condition, so the results are not going to be accurate, 100% accurate. So hopefully you never come across a problem like that on an AP test, but you can just make a comment to that effect to show that you know what's supposed to happen. And if the assumptions are not being met, at least the AP reader knows that you know what was supposed to be happening. Okay, is it normal? We had 30 people in our sample, and we can check it 2 different ways. We can check to make sure that the population is normally distributed, approximately normal, or we can make sure that we have at least 30 in our sample size. And here our sample size is at least 30, so we've met the central limit theorem. requirements, and we are good to go. Okay, the general formula is going to be the stat plus or minus the critical value times the standard error. I'll just put SE right here. So the specific formula is going to be, because this is means, it's going to be X bar plus or minus T star. The standard error is going to be the sample standard deviation divided by the square root of n. And we've just shown we know what we're doing and why. And now we can substitute values in. All right, so our X bar, the sample mean right here, is 17.8. The T star plus or minus, so we did find that before, it's 2.045. And now the sample standard deviation right here is 2 divided by the square root of the sample size, which is 30. So we only use degrees of freedom to determine our critical value, and after that, we are using our sample size. Okay, so now you guys can do that calculation, and we can come up with our critical values. I'm going to put we can put up our confidence interval, that is. I'm going to write the confidence interval while you guys might still be working on it, so you can just check when you're done. Okay, so there's the confidence interval. I'm going to start writing our conclusion, our interpretation of this confidence interval. And again, hopefully you guys are feeling really comfortable with this interpretation and you could write it out yourself. In fact, if you've already done this problem on Friday, you can just be checking the entire time to make sure you got the same stuff. We are 95% confident that the interval from interval from 17.053 to 18.547 captures the true mean number correct on the most recent exam. Okay, and that is really the summary of this entire problem. I'll pause here for just a second before we move ahead. If you have any questions, you can feel free to ask. You can chat them at me privately or raise your hand or just jump in. But assuming everyone is good, I'm going to go ahead and move forward. And the last question, is the professor's claim of 18.5 correct, plausible?
Yes.
Yes, it is. Why is it plausible?
Because the highest value of the confidence interval is 18.55.
Perfect. So there are other inference methods. Thanks for that, Sam. There are other inference methods that we're going to be using where we have different ways of determining if a claim is true or not. And in fact, after this next test, we're going to jump into those. But for right now, it really comes down to if it's within the confidence interval, it's plausible. If it's outside the confidence interval, it's not plausible. So this one is within that confidence interval, and therefore it is plausible. So we can move ahead. So now we're going to look at some multiple choice questions here. And a lot of these are going to be conceptual. We're going to go through like 3 or 4 of them that are calculation heavy. But then the rest, we really need to kind of think through what all the different aspects of a confidence interval are telling us. And I'll have to do some explanation, obviously. Hopefully you can follow along if you've been doing the work up through today, then you should be able to follow all the logic of everything I talk about. But Otherwise, just know that you need to kind of go back and go over this stuff. Okay, so if you got a 99% one sample z interval for proportion that's going to be created from a point estimate obtained from each of two random samples selected from the same population. So you have sample R and sample S. So I'll just put R right here and S right here. R is going to represent a random sample of size 1000 and S is going to represent a random sample of size 4000. If the point estimate obtained from R is equal to the point estimate obtained from S, which of the following must be true about the respective margins of error constructed from those samples? Okay, that's a lot of words right there, a lot of information, but it comes down to the margins of error. We're going to be comparing these two. So let's see. This is, it honestly doesn't say if we're going to be, oh wait, it says it's for proportions. Okay. And honestly, for this problem, it doesn't matter if it's proportions or not, but it is proportions. So the margin of error for R is going to be, it's our Z star. That is, let's see, P hat times 1 minus P hat divided by 1000. But instead of 1000, I'm just going to write N. Okay, so N is going to equal 1000. You'll see why in a second. So for the S, they had a sample size of 4000. So now what I'm going to do is I'm going to do a margin of error for S, which is going to be Z star times, it's the same thing, P hat times 1 minus P hat. We don't know any of these values except we now know that instead of N, it's going to be 4000. N is 1000, so it's going to be 4 times N. So hopefully that you're starting to see why we're just labeling it this way. The actual values here don't matter, except what matters is that we're going to have 4 times the sample size when we get to sample S. All right, so now we can do a little bit of conversion and figure out that over here on the right side, we've got still our Z star divided by, or sorry, but it's going to be times P hat times 1 minus P hat. And then that's all over the square root of 4n. And now I'm going to just jump ahead and do the next step, which is I know the square root of 4 is 2. So I'm just going to erase this. I don't know if I said square root of 2. It's 2 times the square root of n. When I took the 4 out of that and took the square root of it, that's what I'm left with. So I can extract this. I'm going to do one more step and make it look like this. 1/2 times Z star times the square root of P hat times 1 minus P hat divided by square or n, because it's all under the radical. So basically, it looks like when I go from R over to S, S is going to have 1/2 the sample size, or sorry, the confidence interval, 1/2 the confidence interval of R. All right, and this is where it's confusing, okay? It's confusing for me. You might be totally good with it. 1/2 of the confidence of the margin of error for R is equal to the margin of error for S. Because when I substitute margin of error of R in for this right here, that's what I get as my result. Okay. So this is kind of like our bell work. And I did a lot of extra work here just to show very explicitly every step of the way, but hopefully you can kind of reason through this. So now I need to find what answers here. The margin of error for S will be 4 times. Well, I know it's going to be a factor of 2, so it's not going to be this. It's not going to be this. It's not going to be equal. So either margin of error S will be 2 times the margin of error of R, or the margin of error of R will be 2 times the margin of error for S. And this is where you have to kind of reason through it. But what we're saying is that R is going to be bigger. And 1/2 of it will be the margin of error for S. So R is going to be the bigger one. The answer is E. Because half of R will give us S. Okay, so hopefully that was more clear than unclear for you. But if you have questions, we can come back to that one later. Okay, now we're looking at a survey that was done, and we're going to figure out with a 95% confidence interval who would respond very supportive or somewhat supportive of this proposal. Now, one of the first things you need to be looking at for any problem, because you could start putting numbers into problems and really getting confused, you need to determine, first of all, if it's proportions or means. This is a proportion, so it's going to be p hat plus or minus the critical value, z star, times the square root of p hat times 1 minus p hat divided by n. Okay, so that's going to be our big thing. And we want to figure out, first of all, what p hat is. So p hat is going to be, well, let's see, it's very supportive or somewhat supportive. So these two right here. So 336 plus 387 out of the total in the sample, which is right here, 1001 or 1018. And when we do that, we get 0.71. It's 7102. I'm just going to call it 0.71. Okay. And that should work for this problem because we can see right here where the point estimate's supposed to be. 0.71 is what we're working with. We can cross these two out. We know those are not correct. So 0.71 plus or minus z star. This is one that you need to, I mean, it's going to help you if you memorize this one because we're going to come back to this a lot. 95% confidence interval has a critical value of 1.96. Again, like I said at the beginning, if you need help finding critical values, we can talk about that later. And now it's going to be 0.71 is our p hat, 0.29 for our not p hat, and 1018 for the sample size. It looks like we have to do the calculation here just for the margin of error. So we'll do that real quick. And you can see on the screen what I was able to calculate. You can finish your calculations and determine that as well. But we can see what our answer should be. Okay. Hopefully everyone's good with that. All right, so let's move on to the next one. So this one actually is a little more straightforward. It still wants us to calculate a 95% confidence interval. This is dealing with mean biomass in 9 plots of 1 square meter land in a certain forested region. Okay, so mean biomass of the 9 plots is 4.3. So it looks like our sample mean, X bar, is 4.3. Sample standard deviation is 1.5. I know that the formula for this is going to be X bar plus or minus T star times S divided by the square root of N. My sample size right here looks like they only use 9 plots. So this is going to be a little bit weird. 9 is definitely not enough for us to meet the central limit theorem, but they throw this in here to make it all okay. Assuming all conditions for inference are met. So we're assuming this is still normal. Maybe the population is normally distributed. Maybe they did that final method and they checked the actual distribution of the sample and determined it was normal enough. Whatever the case, they have given us that all conditions for inference are met. We don't need to worry about that. So I'm going to start plugging some numbers in. I know that 4.3, well, that would be helpful if I could rule something out, but all of them have 4.3. All right. I know it's going to be 1.5 for the standard sample standard deviation. and 9, so square root of 9. They don't give me 9 as an, or square root of 9 as an option. So I'm going to go ahead and just erase this and turn it into 3, which is the square root of 9. So then I got this t star right here. We'll figure out in a minute. But just with this much information, we can rule out a few possibilities. Anything with the square root in it still can be canceled out. This one has 9 in the denominator, so that's not going to be it. So it's 1.5 over 3. And now we could even use intuition. We don't need to go to the t-table for this. If this was a z star critical value, then I know the 95% z star value is 1.96. But this is a t star, which means it's going to have fatter tails. We need to go out further in order to make sure we're really getting 95%. So 1.96 would be if this was z star, and it's not. So I can really rule that one out. But if I want to, I can actually calculate this accurately and determine that E is correct. But if we did go to the table and we looked at a degrees of freedom 8, which is 9 minus 1, for a confidence level of 95%, we would find that 2.306. Okay. So you can, just to better be safe than sorry, you would go back and double check that. Okay, that's about it here. A medical center conducted a study to investigate cholesterol levels in people who have had heart attacks. A random sample of 16 people was obtained from the names of all patients in the medical center who had a heart attack in the previous year. Okay, and so we've got of the people in the sample. Okay, so we got a sample mean of 264.70. We have a standard deviation of 42.12. Assuming all conditions for inference were met and we're good there, we have a sample size of 16, which means we have degrees of freedom of 15. And we have a 90% confidence level. And now we want to figure out the actual confidence interval. We're not doing like this half step. We really need to go through the entire calculation to find out what that is. Okay, so let's get started. We need to first of all know what our formula is. X bar plus or minus T star with S divided by the square root of N. We know some values, 264.7 plus or minus. I don't know T star yet, so I'll put that in a second. 42.12 divided by square root of N, which is 16. All right. So I can go ahead and do that. 42. I know the square root of 16 is 4. 42.12 divided by 4 is 10.53. Okay, now I'm not even looking at my answer choices. I don't want to try and reduce anything down. I'm just going to go through and finish the calculation. This is where you'd want to go to your t-table, table B that is, and look across for degrees of freedom 15, and then look down the row for the 90% confidence level. And you'll find your number. Now remember, you can also find this on your calculator using inverse T. So that's what I'm going to do real quick. You have to be careful to use the correct area. And I see that my T star, hopefully someone is looking on the T table, the table B, to look at that, 1.753. Okay, so now I'm just going to plug that in, finish the calculation. Okay, so you guys can do that calculation and we'll look at the answer here in a second. So as you are going through, you might be comfortable just calculating one of your two boundaries for your confidence interval, because once you found one of them, it should match one of your answer choices. And if you look at the answer choices, just you'll find something that matches. So there we go. The answer is C. So again, moving kind of fast with this, but that is the full process for finding your confidence interval. And there's just a few things you have to keep in mind as you're going through it, but that's pretty much your answer. Or that is the answer. That's pretty much the full process though. Okay. So let's move ahead. I think that's the last one we have to do that full calculation on until we get to the FRQ. Okay, so this one's going to be another similar problem, but we're determining right off the bat that we are looking for proportions. So I'll just write out my proportion calculation for confidence intervals, which is going to be p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. And I don't know if at this point you kind of like it when you see its proportions because it's a little easier. Maybe you don't think it's easier or harder one way or the other. It's just a different problem. But proportions are, I think, a little bit simpler. So we found that 32% on an e-reader from a sample. So I got 0.32 as p hat plus or minus the z star. It's a 90% confidence interval. This is one you'll probably want to go back to the table to double check. I believe it's 1.645 is a critical value for 90% when it's a z star. And now I can plug in more values. P hat again is 0.32, 0.68, and 1005. So without knowing the critical value, I can rule out two of them, but I need to know the critical value to get the last part of it right, because everything is the same for C, D, and E except the critical value. And there it is. Okay. Now for the rest of these is conceptual, and hopefully that doesn't mean it's more difficult. So the basic idea of this one is that when we look at sample A and sample B, these are means. You can see we've got the sample mean, sample standard deviation, and the margin of error already calculated. And you can notice that the margin of error for sample A is bigger than the margin of error for sample B. So the question is, why is A greater than the margin of error for B? And there's a lot of reasons why it could be the case. We need to find one that makes sense. And before we look at the answer choices, let's remember what affects the margin of error. So if I go to just the margin of error calculation, it's T star times S over the square root of N. So let's just say we want to decrease the margin of error. So anything that we multiply, anything that's in the numerator on this side, and I'm going to rewrite this just a little bit. Anything that's in the numerator, if it's going to be directly proportional to margin of error, meaning as anything up here goes down, the margin of error is going to go down. Anything in the denominator, as that goes up, the margin of error will go down. So that's how we can determine our relationships. Anything in the numerator is directly proportional. Anything in the denominator is inversely proportional. So now if I want a smaller, so why is B smaller? Well, B could be smaller because our critical value is smaller. And the critical value can be smaller if we have a lower confidence level. So here are all the possibilities. We have a lower confidence level. I'll just put CL right here. We have a smaller standard deviation for the sample. So I could have a smaller S. I could have a bigger sample size because as my sample size increases, the margin of error will decrease. So I could have a bigger sample size. Those are the three levers we can pull here that can change the margin of error in a smaller way. So why would B be smaller? Any one of these three reasons. So now let's go to the choices. Sample A is greater. Okay, so well, maybe we should have done it the other way. But anyways, we can still work through this. Why is margin of error for A greater than the margin of error for B? So A is greater than B because A has a greater sample size than B. Well, as the sample size goes up, the margin of error will go down. So it seems like if A had a bigger sample size, it would have a smaller margin of error. So it's not that one. The sample size of A is less than the sample size of B. Well, if that actually seems plausible. So if A has a smaller sample size, then its margin of error should be bigger. So these arrows can flip also. So if your sample size goes down, then your margin of error will go up. So A having a smaller sample size, that would explain that. So that one seems good. So I'm going to circle it. Well, we can always cross it out if we don't like it later. Sample size of A is equal. Well, if they're equal, that wouldn't explain anything. So, okay. The mean of sample A is greater than the mean of sample B. Now keep in mind, we don't use the mean in this calculation at all. Nowhere does the sample mean show up, so that has no effect. And the last one is the standard deviation of sample A is less than the standard deviation of sample B. So this one could be good. Let's see. If A has a smaller, I'm getting all my words mixed up. If A has a smaller standard deviation, then it should have a smaller margin of error because they're directly related. As this one goes down, this one goes down. So if A had a smaller one, it should have a smaller standard margin of error, but it has a bigger one. So that one seems to be opposite of what's happening. Okay. So the only good choice here is B. That one, I know that's a lot to wrap your head around, but hopefully you can kind of work through the logic of that. All right, so this is one, we've got 100 random samples that were conducted by a polling agency. And it's, there's a lot of information here. I'm not going to read it all. Because the basic question is, what's the best interpretation of the 95% confidence level? They're just asking for an interpretation of confidence levels. And remember the example that we did where we generated a lot of confidence intervals? And at the 95% level, about 95% of them captured the true proportion. So we don't know the true proportion, but we can be confident that 95%, or the confidence means that 95% of all of these samples taken will, and confidence intervals created, will capture the true proportion. All right, so we need to find something to that effect. So with 100 confidence intervals, we can be 95% confident that the sample proportion of citizens in the United States who are optimistic about the economy is correct. That doesn't address the kind of the core of it. We're going to see one that looks really good. We would expect about 95 of the 100 confidence intervals to contain the proportion of all citizens of the United States who are optimistic about the economy. That one seems good because they're not saying we're going to get exactly 95, but we would expect about 95 to contain it. The other one says we'd expect about 5 of the 100 confidence intervals to not contain the sample proportion, but they're talking about sample proportion. Keep in mind the sample proportion is inside of every single confidence interval. It's the middle of every single one of them. So that one's not correct. Of the 100 confidence intervals, 95 of the intervals will be identical because they were constructed from the samples of the same size. And that's not true. We're picking different people each time. It's a random sample, so they're not going to be identical. Next one, the probability is 0.95 that 100 confidence intervals will yield the same information about the sample proportion of citizens of the United States who are optimistic about the economy. Okay, so this is not a probabilistic statement when we're talking about confidence level. Or at least not directly like this. And we're not saying that all 100 are going to capture it. So the best answer is B. Out of all confidence intervals created, 95 of them, about 95 will capture it. All right, not much left here. A national survey of 1,501 randomly selected employed adults were asked how many hours they worked per week. Based on the collected data, a 95% confidence interval for the mean number of hours worked per week for all employed adults was given as that. Which of the following statements is a correct interpretation of the interval? All right, we have really good way of answering this one. So we have been using something. We are 95% confident that. All right, so we can already look for something like that. We are 95% confident that, so these two are looking promising right here, that the mean number of hours worked per week for employed adults in the sample is between 41, blah, 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 and 42.63. Okay, well, something's off about that. In the sample, we're not worried about the sample. So let's look at the next one. We are 95% confident that the mean number of hours worked per week for all employed adults is between 41.18 and 42.63 hours. There we go. We're using our sample to make an inference about the population. That looks good. If we read the other three, we'll find that those are not very accurate interpretations at all. So there we go. Okay, another one that's not, it's kind of the same concept, but maybe a little more straightforward. We have a margin of error for a specific sample, but for this sampling, the National Honor Society decides it wants to decrease the margin of error. So to decrease the margin of error, we already talked about this. We have three things we can do. And this is for average number of hours per week spent on homework. I think it's fair to say that we're looking for mean. So we could increase the standard deviation, or sorry, no, those are directly related. Let me change this. We could decrease the sample standard deviation. We could decrease the confidence level, or we could increase the sample size. Those are the only three levers we can pull. So we could, option one says increase the confidence level. Well, that's opposite of what we want. Use the population standard deviation. We can't choose to do that. We don't know that. Use the sample standard deviation. We have to use the sample standard deviation. That doesn't change anything. Increase the sample size. Well, that one seems to be it. Decrease the sample size, and that's not it. So lots of conceptual questions you can see about using these formulas and how one change here or there will affect the confidence interval. So keep that in mind. Okay, and I think, yeah, this is the last multiple choice, and then we're going to look at a couple of FRQs. So we've got a company wants in a confidence interval, they want to have a margin of error no more than 5% with 90% confidence. So what's the closest to the minimum number of consumers needed to estimate with the desired precision? Okay, so we are coming up with the sample size based on the margin of error that's desired. So that's going to be p hat times 1 minus p hat divided by n. Okay, so I know that the margin of error is going to be 0.055%. Z star for 90% confidence level, that's on table B again, and that's going to be 1.645. And I don't know n, I'm solving for that. But then we get to p hat and 1 minus p hat. We don't know p hat. So remember, if we don't know what the actual proportion is, then we're going to assume it's 50-50 because that's going to give us our most conservative estimate. So I'm going to have 0.5 times 0.5. And we're going to and what's going on is how many are going to react favorably to a marketing campaign? What proportion? We're going to assume it's 50-50. Half of them like it, half of them hate it. And now we can do this calculation and we can figure it out. And before I just plug this into a calculator, I'm going to remind you that this is equivalent. And we did this algebra switcheroo right here. It says that the square root of n is equal to 1.645 times the square root of 0.5 times 0.5 divided by 0.05. So now we have all the numbers on the right, our variable on the left. You can do that calculation. Okay. When you finish on the right side, you should get 16.45. That's not even an option. So, but you would want to be careful. They could give that to you like as 17 as a sample size to confuse you, but we know that we still need to square that. So when we square it, we get n equals 270.6025. No matter what decimal we get for sample size, we always round up. So that could be 270.001, and we'd still round up to 271. All right. And now some FRQs. And let me, okay, it worked. So let's look at this. We have a company that makes 3 grades of electrical component. Grade A components have 2% defective rate, B have 5%, C have 10%. And because A is the highest quality, they can charge more, B, they can charge a middle amount, and C, they can charge kind of the lowest amount for that. So they found a batch of components that were known to be of the same grade, but the grade itself is not labeled. So they're not sure if it's A, B, or C, but all of them are the same. And they selected a batch of random sample. They selected a random sample of 200 components, which contains 16 defective components. Okay, so construct and interpret a 95% confidence interval for the proportion of defective components in the batch. So we know the process here. I think it's worth noting right from the beginning that we are looking at proportions. So I'm going to do this somewhat quickly, but SPDC, this is your state, plan, do, and conclude. That format that we started off with today and that we've done a few times, I'm going to do that right here. I need to know what it is I'm looking for. I'm looking for P, which is the true proportion of defective components in the batch. All right. My confidence level right here is going to be 0.95. So already, because it's proportions, I know I'm using Z star. And my Z star for 95% is 1.96. And now I can move on to plan. This is going to be a 1 sample Z interval for P, because I want to find the true population proportion. I need to check my assumptions. Is it random? Is it 10%? And is it normal? Now, let's just start going through. But anyways, it says there is a random sample of 200 components. So yes, it's random. For something like this, I might even want to put a sentence to this effect. There was a random sample, so it meets that assumption. The 10%, this is where it doesn't really tell us how many are in the batch. Here's where we can only assume that 200 is less than 10% of the entire batch. So we could just write something to that effect. I'm not going to write it out because I'm being a little bit lazy here, but you guys could figure out how to phrase that 200 components we are assuming is less than 10% of the number of components in that batch. So 200 is less than 1/10 of n. We're assuming that's true. And normal. Is it normal? This is for proportions. We check this with large counts. So n times p and n times 1 minus p. Now we don't know, it's technically p hat. We don't know p hat yet, but we can figure that out. P hat is going to be 16 defective components out of 200, which is 0.08. And hopefully you guys can figure out, if we do 200 times 0.08, we're going to get back to where we started, which is 16. So 200 times 0.92 is going to give me the complement to that, which is 184. Both of those are greater than or equal to 10. So we have met large counts, and it is normal. Okay, now we're going to start with our standard or generic equation on this, which is the stat plus or minus the critical value times the standard error. I'll just put SE. So my stat is P hat plus or minus Z star times the square root of P hat times 1 minus P hat divided by N. And now I can just start plugging numbers in. These are all found in the problem over here. 200 right here is my N. We already found P hat, so I'll just start plugging in 0.08 plus or minus. Z star was 1.96. The square root of P hat was 0.08 times 0.92 divided by 200, and that's a calculation to do. I'll pause for a second so you guys can calculate that. And I went ahead and put the confidence interval down. And now I'm just going to write our conclusion. The conclusion, of course, is our interpretation. We don't just leave it with numbers on the page. We want to put a sentence to explain what we've got. So we are 95% confident that the interval from 0.0424 to 0.17176 captures the true proportion of, and now we need to put our context, of defective components in the batch. Okay, and we answered part A. Now part A is the hard part of this problem, because once you get that part right, or finished at least, then you can answer the next part. Does the interval calculated in part A allow the company to clearly determine the grade of the component that was produced in the batch? So we need to determine, is this grade A, grade B, or grade C component? Could it possibly be grade A? I guess, could it plausibly be grade A?
Yes, because it's wait, never mind. No.
Okay, no, it could not. Why can't it not be grade A?
Because the interval is from like 4% to like 12%.
There you go, perfect. So if the range of possible proportions is from 4 to 12%, it's not going to be grade A because that's 2% defective rate. So I'm not actually going to write anything out for this, but to answer this, I'd say it can't be grade A What about B? Could it be grade B? So grade B is at 5% and grade C is at 10% defective rate. Can we rule either one of those out?
No, we can't.
We cannot. Okay. So both of those are within the confidence interval. It could have a true proportion of 5% defective rate. It could have a true proportion of 10% defective rate. We don't know which because both of them are within the realm of plausibility. So I would need to write something to this effect. I'm not writing it out right now. I feel like you guys should be able to use your statistical thinking to explain that. These two are within the confidence interval. This one's not, so we can only rule out A. Okay. Last question we're going to go through, and that'll be it for today. So we are going to construct a 99% confidence interval for the mean number of steps taken on a typical workday for all people working in New York City who are an activity tracker. There's the information in the prompt up above. So let's go ahead and go through that process. That's the state plan, do and conclude. Oops, do and conclude. That's the biggest part of this. So we want to find mu, which is the true mean. True mean number of steps for workers in New York City with activity trackers. All right. And we want to find our confidence level. Confidence level here is going to be 0.9 or 99%, I should just say, which leads to a T-star. Well, I'm going to use technology to figure that out. But notice that our degrees of freedom right here is going to be 60 because we have 61. And notice what AP did right here. This is an AP question. They set it up so that you could have an exact degrees of freedom that matches what's on table B. So if you go there, you'll find this value, 99% confidence level, 60 degrees of freedom. You can get that. All right, I'm going to look it up so I don't have to get off of this page. I'm going to use inverse T to figure what that is. It's going to be a 0.005 area with 60 degrees of freedom, which is 2.600. 2.660, I mean. And again, luckily, you don't need to know how to use technology for this. You don't need to know how to find that on your calculator, but if you remember, you can do that. Otherwise, use your table. And let's say it was 64 degrees of freedom. Then you just round it down to 60. Even if it was 68 degrees of freedom, you'd go down to 60 because that's going to give you a wider range. It's more conservative that way. All right, we're good to go with that. Planning. I'm going to use a 1 sample T interval and for mu, and I need to determine if it's random, 10%, and normal. So random, it says, it will say random in here somewhere, random sample right there. So yes, it's random. Is it 10%? I think it's fair to say in New York City, 61 people is going to be less than 10%. All the people wearing activity trackers. I bet there's at least 610 people. So yeah, 61 is less than or equal to 1/10 of our population. And then is it normal? Well, we have a sample size of 61. So n is greater than or equal to 30. So the central limit theorem takes over. It doesn't matter the shape of the population distribution. We will have a normal sampling distribution, approximately normal. All right, we're good on all fronts here. Now let's do. It's going to be stat plus or minus the critical value times the standard error. And in this case, that's going to be x bar plus or minus t star times s divided by the square root of n. We can find those numbers. X bar is right there. Sample mean is 9,797. Plus or minus our t star we calculated already is 2.660. S is the sample standard deviation, which is 2,313 divided by our sample size of 61. And we can calculate from there. Okay, hopefully you guys had time to construct your confidence interval. And now the last part, we are 99% confident that the interval from 9,009.2 to 10,585 steps captures the true mean number of steps for workers in New York City who wear an activity tracker. We do need to specify it's only for people in New York City who wear an activity tracker because we're not sampling anyone who's not wearing an activity tracker. Okay, fun times with that. There is a part B. So let's look at that real quick. A wellness director at a company in New York City wants to investigate whether it is unusual for one person working in the city who wears an activity tracker to record approximately 8,500 steps on a typical workday. Is it appropriate to use the confidence interval found in part A to conduct the investigation? And this is a conceptual one, something we haven't really talked about, but now it's good that it's coming up. Keep in mind what a confidence interval is for. We have, I'm going to imagine this as a number line, right? So I've got a number line, I've got 9,009.2, and then 10,585 up here. So what I'm saying is somewhere in this interval, I'm not saying anything about an individual person. I'm saying somewhere in here, my true mean, population mean lives. Now, this says nothing about individual behavior because you will definitely have individuals in New York City who are outside of this range. You will have someone in New York City who is living right here at that 8,500 level on their steps. So individuals can be outside of this range, no problem. But when you average, when you take a sample of size 61 and you have a 99% confidence level, then the proportion, in this particular case, the true, not proportion, the true mean number of steps taken is going to live somewhere in this range. So this only says something about the population mean, not about individual behavior. You're also going to have people up on the high end that are outside of this range, but that doesn't matter. Okay, So that is really what's going on with this. So this would not be appropriate. The short answer to that question is no, it would not be appropriate to use a confidence interval because a confidence interval is only useful for identifying where the population mean is, not where an individual is. Okay. So there we go. Good times. Those are our FRQs to look through. All right, and there we are. Your homework, there's no homework to turn in tonight, but there are review materials. And in fact, I need to go over to the Canvas page to show you this stuff real quick. Additionally, there was a problem that was pointed out to me. If you tried to turn in your progress checks before, it wasn't actually an assignment you could turn in. It is now. So if you completed those, just let me know and you can turn in your done. But on the Canvas page, this is the last thing I'll do and then you guys can leave. There's a reference posters, which are for every single unit. I post some things there that might be helpful for you. Reference documents right here. We've got 4 things. There's formula study sheet. This is a blank one up on top and then one that's been filled in. So you can use it if you want to like print this off or something and fill it in yourself, that's helpful. Same thing with the big ideas and the key right here. These are both for your reference. You can just pull them up tomorrow if you want to. Sample size practice. This is going to be useful if I say, hey, we want to have a margin of error of 0.03. What sample size is needed? You can practice with that. Here's the key. And then this is going to be more practice with those, the full process for coming up with a confidence interval. So these are all here with answer keys. I highly encourage you to look through that. And I highly encourage you to do the progress checks for 6A and 7A, which are going to give you more multiple choice practice. So if you have any questions, you can stick around. Otherwise, you can have a wonderful day.